Hey everybody, welcome to today's lecture 10 of the Analysis of Algorithms course. And today's lecture is on shortest path trees. It's based on section 6.1 and carries on from a lot of the work we've been doing. Okay, so let's first define the problem. So you guys have been busy with the snake game, so you've probably looked at shortest path algorithms a little bit. But let's say what you wanted to do was find the shortest path from some vertex in a graph to every other vertex. So if we look at the graph over here, perhaps what we want to do is find the shortest path from vertex 0 to every other vertex, or from vertex 1 to every other vertex. Well, so what would you do? Now, when I ask this in in-person classes, the most common answer is, well, we can do a breadth-first search, right? So what happens with the breadth-first search is that it tries to make shorter, wider trees, right? So I hope you've all read that section. If you haven't, please do. Breadth-first search is one of the algorithms you're very likely to use in your snake game anyway. But basically what it does is that because it goes sort of across before it goes down, it ends up with shallow trees, like as shallow as possible. And because it's making them as shallow as possible, it's actually finding the shortest path from the root to anywhere else. Okay, so as an example, let's say from this graph, we constructed this breadth-first search tree, right? If you're not sure how to do that, again, please go back to the section on breadth-first search trees and read it. This is a very important algorithm. Okay, so with the breadth-first search tree, it would have said, okay, well, 0 has the neighbors 1, 3, and 4. So we put those at the next level. And then expanding from 1, it's got the neighbors 2 and 5. And then that's our entire tree, right? It just expands until we run out of nodes, and we've run out of nodes. Now, let's take one of the relatively long paths, the path between 0 and 2. It goes 0, 1, 2. Now, if there was a shorter path between 0 and 2, it would have to be the edge 0, 2. So this edge 0, 2 would have had to exist, right? But if the edge 0, 2 existed, then when we were looking at 0's neighbors, we would have found 2 and put 2 over here. Right? So the only reason 2 ended up deeper in the breadth-first search tree is because there's no edge from 0 to 2. So that's just an example of how breadth-first search tree actually finds the shortest possible path between the root and every other vertex, right? So 0, 4, 0, 3, and 0, 1 are clearly the quickest ways to get to 1, 3, and 4 from 0. But it's interesting that that's true for 2 and 5 as well. Okay? Now, this breadth-first search then gives us basically the answer. So I guess that's the end of today's lecture. No, I'm kidding. I hope you didn't switch off, although if you did, you wouldn't hear this part either. But the question we're going to concern ourselves with today is, what do we do if it's a weighted graph? So here, when we said a path was the shortest path, we just meant it's the least number of edges to get from 0 to our target, or to get from the root to whichever vertex we're trying to get to, right? But if we have a weighted graph, then it's a little bit different, because now, for instance, if we wanted to find the shortest way to get from 0 to 3, it's not necessarily the edge 0, 3. It could be 0, 1, 3 or something, because the edges have different weights, right? So we're trying to find the path that has the least total weight rather than the least number of edges. Okay? Now, how would you do that? Now, one intuition you might well have is, maybe we can use the minimum weighted spanning tree algorithm. Maybe we could do the same thing as that and just pick the cheapest path at each go, right? But the minimum weighted spanning tree of this graph looks like this, right? So this is if we started at 0, or let's say we started at 3 randomly, and we just picked the cheapest edge going from a vertex in the tree to a vertex not in the tree, in the same manner as last week's algorithm. What would have happened is we would have ended up with this minimum weighted spanning tree. Now, that minimum weighted spanning tree looks cool. It's definitely got a smaller weight than this, but does it have short paths? Well, the thing is, the minimum weighted spanning tree algorithm doesn't care about finding short paths. It just cares about finding the smallest total cost for a connected subtree, right? So, as an example, let's look at the vertices 3 and 4. If I were to traverse from 3 to 4 in my minimum weighted spanning tree, I'd have to go 3, 1, 0, 4, which would cost me 3, 6, 7, right? But there's clearly a cheaper path than that. I can go from 3 to 4 just by using the edge 3, 4. Okay, so this tree doesn't represent the shortest path from 3 to everywhere. Okay, so the minimum weighted spanning tree is the wrong thing to use, and it's the wrong thing to use because it only cares about the total cost of the edges, not the costs of the individual paths. Okay, here's another example. Let's say we had this original graph. It's just got edge 1, 1, 1, 1, 1, 2, right? These are the costs. If we constructed a minimum weighted spanning tree rooted at say 0, we'd find this edge as the cheapest edge, then this one is the cheapest edge, then this one is the cheapest edge, this one is the cheapest edge, this one is the cheapest edge, and we'd eventually have this tree. But what's the shortest path from vertex 0 to vertex 3? Should it actually cost 1, 2, 3, 4, 5? No, it should just be the edge 0, 3, right? Because that would only cost us 2. Okay, so the problem with this is that the minimum weighted spanning tree algorithm is greedy. It just keeps seeing this edge that costs 1 and it's like, oh, that's awesome, I'm taking it, right? It doesn't care about the consequences in the future. Now, what we want to do is we want to change that greediness. We want to make it care about consequences. So what we do is we say, don't just pick the cheapest edge at each step, which is what the minimum weighted spanning tree is. Pick the cheapest edge cumulatively. So pick the edge with the lowest cumulative cost. Okay, what do I mean by that? What I mean by that is that when I'm picking an edge, let's say I'm going from 0 to 1, I'd say, well, the cumulative cost is 1 because it's just the edge 0, 1, right? But then from 1 to 2, the cumulative cost is now 2 because it cost me 1 to get from 0 to 1 and then another 1 to get me from 1 to 2. Okay, similarly, the cost of this edge is not 1, it's 3, because in order to take this edge, I had to go through these two edges first, right? So I had to go this way, this way, this way, which would have cost me 3. Okay, and that's pretty much the only difference between Prim's algorithm, which was the minimum weighted spanning tree algorithm we did last week, and Dijkstra's algorithm, which is the shortest path algorithm we're doing this week. Okay, so it's not a super huge extension to the algorithm we did last week. Basically, all we're saying is instead of picking the edge that's the cheapest, we instead pick the edge that's the cheapest cumulatively, meaning the cheapest to get to the start of that edge and then plus the cost of the edge itself. Okay, so let's look at how that would play out in this example. The first thing is what we're going to do is keep the cumulative cost of getting to a vertex to make it easier for us to do our calculations. So we're going to say if the root of our shortest path tree is 0, then the cost of getting to 0 is 0, right? Then we pick the cheapest edge available to us in terms of cumulative cost. So this edge will cost us 1 and this edge will cost us 2. So for this step, it's similar to the minimum weighted spanning tree algorithm, and we're going to pick this edge, which costs us 1. But now what we do is we say, well, look, the cost of getting to this vertex is now 1 because I had to take this edge. Okay, then the next thing we do is we're picking what's the cheapest edge to pick next. Now the cost of this edge 1, 2 is 1, but it cost us 1 to get to the start of the edge. So now the cost of this is 2. Okay, and the cost of this is also 2. So now it doesn't matter which one we pick. We can pick either edge. We'll just, for interest's sake, say whether we picked this one. We may well have picked this one, but we didn't. They were equal, so it didn't matter. So we picked the edge 1, 2. The cost of getting to 2 is now recorded as 2 because it cost us 1 to get to 1 and then another 1 to move across to 2. Now the next choice we have is that we can either pick the edge 2, 5 or the edge 0, 3, right? Now the edge 2, 5 is going to cost us 2 plus 1, which is 3. And the edge 0, 3 is going to cost us 2. So the cheaper one is to pick 0, 3. Okay, so you can see how this differs now from the minimum weighted spanning tree algorithm. Because in the minimum weighted spanning tree algorithm, we would have picked this edge because we don't care about this cost so far. Okay, so we picked that one, which cost us 2. And so the cumulative cost of getting to vertex 3 is now 2. Okay, next we can either pick the edge 2, 5 or the edge 3, 4. Okay, 2, 5 will cost us 3. And 3, 4 will also cost us 3, right? Both of them are 2 plus 1. So we can pick either one. We're just picking 3, 4 for the hell of it. And 3, 4 costs us 1. So the total cost of getting to 4 is now 3. Okay. And our next choice, we can pick the edge 4, 5, which will cost us 4, or the edge 2, 5, which will cost us 3. So we're going to pick the edge 2, 5, which costs us 3. And now all our vertices are in the tree, and so we can stop. Okay, but so this tree looks quite a bit different from the minimum weighted spanning tree one, in that now, if we wanted the cheapest way to get from 0 to 3, we would correctly pick the edge 0, 3 as the full path, right? Instead of going all the way around. Okay, so but this was quite an informal way. Let's make it a little bit more formal. So we say, okay, start off with the root vertex and then repeatedly add the edge with the lowest cumulative cost from the original graph, going from a vertex in the tree to one not in the tree, and stop when you have all the vertices from the original tree. So it's pretty much the same as the minimum weighted spanning tree algorithm, except I've put cumulative here. But that's going to mean that our implementation is going to be very different. So we're going to need some data structures. So the first one is we need a parent array. That fundamentally stores the answer. If you remember from the first lecture on trees, the parent array is our representation of a tree, right? It's just how we keep track of what edges are in the tree. We need a cost array, and this is basically keeping these blue numbers, right? It's keeping the cost of getting to the edge, okay? But at each point, it doesn't, while we're busy running the algorithm, we don't know the cost to the edges. So what it keeps in here is our current best estimate of getting to that edge. It's not necessarily that we already have the cheapest path to that or the shortest path to that vertex, but it keeps our current best estimate of what it'll cost us to get to that vertex. The marked array stores whether the vertex is in a tree, because remember we said it has to be going from a vertex in the tree to one not in the tree. So we have to know whether a vertex is in the tree, and the easiest way to do that is to just keep a Boolean array that stores whether items are in the tree. Okay. Now, this part of it is still not particularly concrete, so let's make the algorithm more concrete. So what we want to do is, we have to pick a root vertex, right? And this is quite important. In the minimum weighted spanning tree algorithm, which we did last week, it didn't matter which vertex we chose as the root. Whichever vertex we chose, we're going to end up with the same minimum weighted spanning tree, and it just didn't matter. For the shortest path algorithm, it does matter, because the algorithm will find the shortest path from the root to every other vertex, right? So if you pick, for instance, 1 as the root, then you'll get the shortest path from 1 to every other vertex, right? But so if you wanted to know the shortest path from 3 to 4, the tree won't give you that, because it only gives you the shortest path from 1 to every other vertex. So when you pick your root, you must pick your root to be the vertex that you care about the shortest path from. Okay. And what you're going to do is you first set marked of root to true, because marked keeps track of whether that vertex is in the tree, right? And the root is in the tree, so we set it to true. We set the parent of the root to be the root itself. That just lets us know that that is the root, right? There's nothing, it has no parent, okay? And we set the cost of the root equal to 0, because we're already at the root, right? We're trying to find the shortest path from the root to every way, and the shortest path from the root to the root costs 0, because we're already there. Okay, does that make sense? So let's start off with the same graph we had earlier. Yeah, there's not much there. It's just the vertex 2 and 5, which my head is going to block, but you can just remember that there's 2 and 5 there. Okay. Yeah, the actual slides are uploaded as well, so if you want to keep them open on the side so that you don't get confused by my very large head, you can keep those slides open on the side. Okay, so we're initially we're looking at the root being 3. We could pick any other root. It matters in that the tree would be the set of paths from the root downwards. So we're saying we want the shortest path from 3 to every other vertex, right? So we pick our root as 3. That means we set the cost of 3 to 0 and the parent of 3 to 3 itself, right? So it has no parent. Then repeatedly Okay, now then set the cost of v equal to the cost of root comma v for all v. Okay, what does the cost of root comma v mean? Okay, so we're saying set the cost of every edge. Let's take, for instance, 0. Set the cost of 0 to be equal to the cost of the edge going from the root, which is 3, to the vertex 0. So it's the cost of the edge 3, 0. Okay, now if we look at that, there's a cost of the edge 3, 0, which will cost us 6. So basically we're going to set the cost of getting to 0 to be 6. Okay, but basically what it's saying is that we're looking at every neighbor of 3, and we're updating its cost to be the cost of the edge to the neighbor. Okay, now that's the same as doing this, simply because, like, we're saying the cost of getting to any vertex is the cost of the edge between the root and that vertex, right? But for the ones that are not neighbors of 3, there is no edge, so we can't update their costs. Okay, when I put -1 here, it just means unknown. The cost is unknown and the parent is unknown. Okay, so we're setting the cost of v equal to the cost of root comma v. So initially when we look at vertex 0, we're saying, well, there is a path 3, 0, right? The edge 3, 0 forms a path, and the cost of that path is 6. So that means we set the cost of 0 to 6 and the parent of 0 to 3, because now, you know, its parent in the tree will just be 3 directly. Okay. Then we say for the next vertex, which is 1, we're saying the cost of getting to 1 should be the cost of the edge 3, 1, which is 3. Okay, so we set the cost of 1 to 3 and the parent of 1 also to 3, which is the vertex number, right? Then for vertex 4, we say set the cost of vertex 4 to 4 and the parent to 3. Okay, so you can see what we did there. We just updated the costs of all the neighbors to be the cost of the edge from the root there. Okay, then under this repeatedly part, this is where things get a bit interesting. So we had set the marked of the root to true, just basically to say that it's in the tree. Okay, now what we do is we find the unmarked vertex y that has the lowest cost. Okay, so which vertex here has the lowest cost? Well, strictly speaking, it's vertex 3, right? But vertex 3 is marked because it's already in the tree. Okay, so it's green, which in this terminology means marked. That's in no way a standard. That's just something I made up. But vertex 3 has the cost of 0, which is the cheapest, but it's marked, so it doesn't count. So what's the cheapest unmarked vertex? Well, my candidates are 6, 3, and 4 of these costs. So 3 is the smallest number. So vertex 1 is the cheapest one. Okay. Everyone happy with that? It's so confusing lecturing to no one. Like, I'd normally look at you guys until someone either said yes or no, but I'm going to assume everyone said yes. And I hope I'm not wrong. In fact, it'd be kind of funny if you all just simultaneously looked at your screens and said yes. But I found the unmarked vertex with the lowest cost. It was vertex 1, right? Because that cost 3. And then what I'm going to do is I'm going to set its marked value to be true. Okay. So now that means it's in the tree, because marked kept track of whether something was in the tree. Now, when it's in the tree, what I have to do is I now have to see whether I've found any new paths by adding vertex 1 to the tree. So what I'm going to do is I'm going to look at all of its neighbors, and 1 has every vertex as a neighbor. Okay, so 1 is next to vertex 0, vertex 4, vertex 2, and vertex 5. Okay, so then I'm going to say, okay, well, 1 is in the tree right now. When I look at this edge that it has, 1, 0, that implies that now there's a path there, right? Because if I wanted to get from 3 to 0, I could go from 3 to 1 and then 1 to 0, right? So what I want to know is that cheaper than my current estimate of getting to vertex 0? right? So by adding vertex 1, I want to now see if it leads to any cheaper paths than the ones I found before. So what I say is, I find the edge yz, which in this case is 1, 0, and see if we found a cost that's cheaper than the current cost, right? So to know the cost of taking the edge 1, 0, remember I care about the cumulative cost. The cumulative cost is the cost of getting to 1 plus the cost of the edge. Now the cost of getting to 1 is here in the cost array, right? It's 3. So the cost of getting to 0 must be 3 plus 3, which is 6. Okay, and the current cost is 6, so I'm not going to do anything. Okay, I haven't found a cheaper path. I found a path that has the same cost. Okay, let's look at the next vertex, 1, 2. Okay, now my cost of taking the edge 1, 2 is the cost of getting to vertex 1, which is 3, plus the cost of the edge 1, 2, which is 4. So the cost is now 7 of getting to vertex 2. And my current cost is unknown, which means I have found a better cost. So I'm going to update vertex 2's cost to be 7 and its parent to be 1, right? Because that's the vertex that the edge leads from. Okay, that's the vertex I'm looking at right now, basically. Okay, so when we looked at 1, 2, we updated a cost. Now let's look at the edge 1, 4. Okay, the cost of taking the edge 1, 4 would be the cost of getting to 1, which is 3, plus the cost of the edge 1, 4, which is 4, so that would be 7, right? But if I look at the current cost of getting to vertex 4, it's only 4. So this new path that I found, which costs 7, is not cheaper. Okay, so I'm going to keep my current cost and my current parent. The next thing I'm going to look at is the edge 1, 5, which costs 2. But the cumulative cost of it is the 3, which is what it cost me to get to 1, plus the 2, so it costs 5. The current cost of getting to vertex 5 is unknown. So that means I have found a cheaper cost. So I'm going to update the cost of vertex 5 to 5 and its parent to be vertex 1. Okay, so I went through this for loop that said for every unmarked neighbor, which were these blue ones, and I updated all of their costs. Well, I mean, for some of them I didn't update it because it didn't need updating, but the point is I at least checked whether they needed updating. Okay, and this thing said stop when all vertices are in the tree. Are all vertices in the tree? Well, no, because if they were, all of these would be true, right? So that means I go back to the repeatedly. Okay, so then it says find the unmarked vertex y with the lowest cost. Now when I look through this list, the cheapest vertex is 3, which costs 0, but it's marked. Then 1, which costs 3, but that's also marked. So of the ones that are left, the 6, 7, 4, and 5, the cheapest is the 4, which is vertex 4. Okay, so that means the next thing I'm going to add to the tree is vertex 4. So I set marked of vertex 4 to true, and then I say for every unmarked neighbor z, and its unmarked neighbors are 0 and 5, right? Those are the ones it has an edge to. Okay, so let's start off with 0. So the cost of the edge 4, 0 is 1, but its cumulative cost is the cost of getting to vertex 4, which is 4, plus the cost of the edge 4, 0, which is 1. So the cumulative cost is 5. Now my current best known cost is 6. So that means I've actually found a better cost. Okay, so what that means is I've basically found a better path to 0 than the path I already know. The path I already know is this 3, 0, which costs 6, and now I found 3, 1, 4, 0, which costs, now I found, 3, 4, 0, which costs 5, right? So this path which costs 6 has been overtaken by this path which costs 5. So what I do is I update the cost to now be 5 and the parent to be 4. Okay, so this becomes 5, this becomes 4. Okay, and it's just following this algorithm here. Okay, and for the other edge, which was 4, 5, my cumulative cost is the cost of getting to 4, which is 4, plus 8, which is 12, right? So my current cost is 5. Since the new cost I found is 12, I don't update this because the one I have is cheaper, right? So I haven't found a cheaper path. Okay, and that means I'm done with this for every unmarked neighbor, and I check are all vertices in the tree. Nope, so I go back to my repeat, right? And it says find the unmarked vertex y with the lowest cost. That now is between 0, 2, and 5. Those are the unmarked ones, which cost 5, 7, and 5 respectively. So the cheapest one, it's a tie. I can either pick vertex 0 or vertex 5. They both cost 5, and it really doesn't matter which one I pick. So I'm going to pick vertex 0, which costs me 5. And then it says for every unmarked neighbor z. But if I look at this, it doesn't have any unmarked neighbors. All of its neighbors are marked. So that for loop is not going to do anything. So I'm done with looping for vertex 0. Then it says stop when all vertices are in the tree, but there's still some falses in here, so I can't stop. So then it says find the unmarked vertex y with the lowest cost. Now my unmarked vertices are 2 and 5. 2 costs 7 and 5 costs 5, so the cheapest one is actually 5. So I pick vertex 5, and then it says for every unmarked neighbor z. Does 5 have any unmarked neighbors? No, it doesn't. So again, the for loop does nothing. And the next thing says pick the cheapest vertex. That's find the unmarked vertex with the lowest cost. And there's only one unmarked vertex, was vertex 2. So now I pick it. And then I say for every unmarked neighbor z, and there's nothing in there. So there's no unmarked neighbors. And then stop when all vertices are in the tree. Now, when I look at my marked array, all items are true, which means all vertices are in the tree, and I'm done. Okay. When I'm done, I've ended up with a parent array which represents my tree. So 4, 3, 1, 3, 3, 1. Okay. But what does this thing mean? How do you read this parent array? We did go through it in a previous lecture, but I'm just going to go through it again. So when I look at this parent array, I can see there's one vertex whose parent is itself. That means that one is the root because it has no parent. Every other vertex has a parent. Vertex 3 has no parent, so that means it must be the root. Okay. Then I can see 2 other vertices whose parents are 3, vertex 1 and vertex 4. So those are the children of 3, right? Vertex 1 and vertex 4. Okay, and obviously the cost comes from the edge 3, 1 and the edge 3, 4. Okay. Then vertex 1 I can see is the parent of vertex 2 and vertex 5. So that means I've got vertex 2 and vertex 5 over there, and vertex 4 is the parent of vertex 0. So this is my shortest path tree. Okay, so that means I've now found the shortest path from the root, vertex 3, to every other vertex. Now this is probably one of the most commonly used algorithms in computer science. It's an algorithm you're going to see over and over again. I mean, no matter what you do, you're going to see it if you do machine learning, you're going to see it if you do security, you're going to see it if you do anything, right? Shortest paths are just one of the things you just always have to find. So it's an algorithm that's quite important to understand. And the resource in the book is quite good as well. I've tried to be quite informal in the lecture, but if your preference is, for instance, for things to be quite formal, the book does have a pretty good formal explanation of this. There is also lots of code. I mean, like I said, this is one of the most popular algorithms out there. It could be worth attempting to code for yourself, because then that's when you know you really understand something, is when you code it. But otherwise, even if you read through the code, I think there's code in the book for it, but also there's lots of code on the internet that covers it. Okay. So, but definitely don't neglect this algorithm. It's super important. Okay, I hope you enjoyed the lecture. This week's exercises will reinforce what's in this lecture. So yeah, don't neglect it. Also, if you've been struggling to get responses from me on WhatsApp, it's because I fundamentally broke my phone, and now I've switched between the phones that I replaced it with, so I've lost a lot of messages. So if I haven't responded to a message of yours, please re-message. Okay, thank you everyone.